Hi, and welcome back. Today we're going to be talking about Thinking Like a Chemist, Chapter 1.3. Let's first look at the lesson objectives. We want to describe how Lavoisier transformed chemistry. He's often called the father of chemistry. And we want to explain the role of collaboration and communication in science. So let's look at this kind of moldy piece of bread. We see a lot of green specks on it and some of the black area on it. But what we noticed is if we were Alexander Fleming, he noticed this too. He observed this. He made an observation. But he also noticed that the bacteria, the black part, wasn't growing anymore. And it sort of seemed that the blue fungus was somehow keeping the bacteria from growing. So other scientists have seen this phenomenon before, but it was the first time that someone actually noticed that this might have some properties in keeping bacteria in bay. It ultimately led to the creation of penicillin. So what was the observation? The observation was that this black area was not growing in the presence of this yellowish-green mold. Okay? So he hypothesized the bacteria is not growing because the yellow-green mold is releasing a chemical that prevents bacterial growth. So observation is just observing what's happening. Hypothesis is giving a possible explanation for why that happens. So you have observation and hypothesis. Hypothesis, at this point, we're in the realm of philosophy. We have to do something else later on to test this, to see if we actually have the truth with this. So let's talk about Antoine Lavoisier. Lavoisier was a chemist. Oops. Well, actually, he had a day job. He was a tax collector. And he was the tax collector for the King of France right before the French Revolution. So that will come in part of the story later on. But Lavoisier, on the side, was a pretty good scientist. And he basically changed chemistry, or alchemy at the time, from a science of just observation to science of measurement. And I'll explain how he did that. But first, let me tell you a little story about Lavoisier. As I said, Lavoisier was around at the time of the French Revolution. And tax collectors, number one, weren't the favorite of the people to begin with. Secondly, Lavoisier could not put up with anyone that was not thorough and scientifically inclined. So one day, this person who liked to hypothesize all the time said, I think that Lavoisier guy is pretty smart. I want to work for him. So he went over to his house, knocked on the door, and Lavoisier, he says, I want to be your apprentice. And so Lavoisier asked him a couple questions. The guy absolutely knew nothing about what Lavoisier already knew. So he says, come back when you've learned something. This got the guy really, really upset. So he went to the people who were involved with the French Revolution, not the royalists, the people that were chopping people's heads off. So this Lavoisier guy, he's a tax collector, and he's no good. So they went, arrested Lavoisier, and eventually guillotined his head off. He was only in his 30s. Imagine all the things that could have been done if Lavoisier had survived. Now, Lavoisier really did leave a legacy of many things, but this gives you the idea that chemistry is not alone. It is part of the history that's going around us. Scientists work on projects that are allowed by the government of the country they live in. Some scientists have to leave their country because they're being persecuted for other reasons. So science is not just by itself. It's influenced by all the other things you learn in school. So let's look at observations. Okay, science was observations. So we just talked about, for instance, we talked about the bread with the mold growing on it. Let's look at some observations. What's some observations that Lavoisier made? Well, Lavoisier was interested in the masses of different elements. Now, what really made Lavoisier important is, at the time, they really didn't know what caused things to burn. They just thought there was some sort of substance in the air that was required for things to burn, which was true, but Lavoisier noticed that whenever he burned something, a lot of times the mass of that something increased. And so he said this has to do something with it. So he observed increases in mass. So increases in mass when something's burned. Okay? Now, actually, if we think of mass, mass is a measurement. So he measured mass. And he could do this very, very accurately. He could do this to the 0.005. Oh, one more zero. So 0.000, so 3 zeros, 5 grams. So he could tell a little bit of difference. So that was really what he was doing. Up here, you could say that, you know, when something burned, you required eventually flame went out. So something was being used up, okay? And other people describe that as some sort of mysterious substance called phlogiston. Well, he figured that it was either nitrogen or oxygen that was doing that because he had already discovered those two things. So by measuring the mass, he could show that there was something reacting with the substance that was being burned. And that was going to be oxygen. So this was going to lead us eventually to the idea of the conservation of mass. Okay. Scientific inquiry is planned and deliberate investigation of the natural world. So you have a hypothesis. You first have some observation. You have hypothesis. Now you have to design experiments. So what are you going to do first? Let's look at the steps that we want to look at first. All right? So we can look at this. All right. What would you do first? Okay, let's think about it. Asking questions, formulating hypotheses, making observations, developing theories, testing hypotheses. Okay, you can, actually there's two things, okay? These are the first two things you're going to be interested in. You probably saw something, or maybe you asked questions. So you might, I would say, I probably would do observe something, and then I might have some questions about it. Okay, then I might say, well, the reason that occurs is that they have hypotheses that are forming. Okay, and then I'm going to test these hypotheses, and eventually we'll just look at a theory. Okay, so we basically see something, we ask some questions about it, we then kind of basically have to form a hypothesis of what's happening. We test it, and then there we go. So we have making the observations first, then we ask some questions about it, we formulate the hypothesis, and we test the hypothesis, then have a theory. That's basically the steps of the scientific method. What is another word for testing hypothesis? Anybody know? That would be experiment. So experiment would be the next step. Experiment is going to be the fifth step. The fourth step. Okay, now when we experiment, we have different sorts of variables. We have what's called the independent variable and independent variable. The independent variable is the thing that is being manipulated. Okay? And sometimes it's called the manipulative variable. And the dependent variable is often called the responding variable. So this is the thing the experimenter changes or manipulates. And this is what then responds to that change. Okay, so for instance, if we want to see how much sunlight influences the growth of a plant, we could have a plant and keep one plant in a closet. Another plant we would bring out for 5 hours every day and then put in a closet. And maybe a third plant we would keep outside the whole time. So what we're changing is the amount of sunlight the plant gets on a daily basis. So that would be the independent variable. What we're measuring, okay, so the responding is the one we measure, would be how much the plant grew. So that's what a dependent or responding variable is. It's going to be something you can measure. So if we go back to Lavoisier, there we can see science is becoming a measuring system, a measuring science. So if I wanted to find out how something affects something else, the dependent variable would be, and the independent variable would be. Okay, so let's think about that. What would you put there? I gave you one example. So, for instance, what I would say is if I wanted to find out how the amount of sunlight affects the growth of a plant, the dependent variable would be the growth of the plant, and the independent variable would be the amount of sunlight. Okay? So another thing we want to talk about is models. Okay? Models are something that represents an object or an event. Okay? They could be physical, mathematical, or conceptual. So sometimes we use math to show it. We use computer to show it. We use a concept. We know things like airplanes are really big. If we wanted to look at an airplane, we might design a smaller model. An atom is very small, so we might make something bigger to see it. We might use math to explain how an electron goes around a nucleus. What's some advantages of models? Okay, they probably cost less than having a huge airplane to look at and study. We can actually use a model. They're probably easier to manipulate. You can move them around much more easily than if they're very small or very large. You can control the model without outside influences, only the things you want to do with it. It's easy to repeat the trial. If it's smaller than something that's big, you can do it more frequently. If it's larger in hand size, you can do more things than if it's really small. And you can see it. If it's too small, you can't see it. Collaboration. Why is collaboration important in science? Collaboration, we have to work together to solve problems because everybody has different ideas. Now, there's benefits and there's problems with it. Okay, so let's look at some of the advantages and disadvantages. One is you share ideas. You have somebody to talk to. You can share resources. You might have one piece of equipment and other scientists might have another piece of equipment. You can share work. Some person can do part of it, another person can do the other, and then you bring it together. And you can share your knowledge and background. You may have slightly different knowledge bases and different backgrounds. You bring that to the table. The disadvantages, of course, is one person may be working harder than the other. People may not give you credit, or that you might not give them credit, and you might not get along with the other person. So that's some disadvantages of not working with someone else. But usually the advantages far outweigh the disadvantages. The other thing that's important with scientists is that they're able to communicate with one another and with the public. They have to take their scientific speak and be able to translate it into something the public can understand. And they also have to talk at a level with other scientists and be able to communicate with them about what they're doing and why they're doing it. Okay, so the last thing I really just want to go over one last thing and talk about theories and, okay, one last thing I want to talk about is theories and laws. And this is often an area of confusion. A theory comes about after many experiments, okay? And it's been verified. A law could be mathematical explanation, or a long, long period of time been disproved. So in other words, they're related, but they're different, okay? A theory comes about after you do an experiment. It's been repeated. It seems to work most all the time, and we pretty much say that the theory is now accepted, okay? So it's well-tested explanation for a hypothesis. A law, on the other hand, it basically can lead to, a law sometimes, but it's a concise statement that summarizes the results of many observations. So in other words, a theory will be explained by experimentation. A law is more of a summary of this, or it's basically something that is observed and it's known to be true and we can prove it through math. So it's a little bit different. There's a little bit of vagueness between the two, but that you should be able to, theory comes after experimentation, after repeated experimentation. A law can arise as a summary of several years of a theory not being disproved, and it seems to be set in stone. Okay, and we'll talk about the atomic theory later on and see how that has changed with time and probably will continue to change with time, whereas something like the law of conservation of mass is pretty steady. That's it.